Hello everyone. In the previous lecture, we had a look into seismic refraction methods. Toward the end of that, we had seen this particular slide wherein we are trying to understand the efficacy of the ground improvement procedure which we had carried out in one of the site near Chennai, right? It is an excavation site for construction of a major building, right? Over there, I told you in the previous lecture, there was a weak zone as indicated between these red lines, and also at another site where we had carried out a foundation strata mapping, we came across sites where there were some weaker zones, right? This is what you see, right? We have massive rock on either end, right? Whereas in between there is a weaker rock. So over there, we recommended for improving the ground. As you see in this diagram, right, ground improvement is done by injecting cement grout through the boreholes, and the grouting which we have injected is forced to enter into the formations from the borehole. And once if it consolidates, it improves the ground as you see in the diagram. That means previously we had lot of weaker zones. The weaker zones are now filled with the grout which is the cement slurry which we have injected in. So thereby the ground is improved. And we can also use seismic refraction survey to understand how effectively we have carried out the ground improvement. Right? How can we do that? We can do that by repeating the seismic refraction survey. That means before ground improvement, what was the shear wave velocity? After we carry out ground improvement, how the velocity has improved. That is what we are going to do. Right? So, how we carry out the ground improvement, right? Ground improvement is carried out by improving the ground by injecting the cement grout, as I said previously. In this case, grouting is done by substages. That means stage wise we are trying to improve the ground. That means we drill the well, right? Bore well is drilled. Then we use a packer to seal off a particular zone, right? We use a packer, and through the central annular space, cement is pumped in so that the cement is injected to the either side. So this is how now we have packed or grouted this region. After having grouted this region, we will allow the cement to settle down for some time. Then we lift the packer. These are known as packers, which are nothing but inflatable balloons, right? That means the drilling rod or the rod through which we inject the cement grout appears like this, which has got a kind of a inflatable packer. It is something like a balloon. This balloon will be inflated with a special gas so that it, when the air is pumped in, it gets inflated like this. The idea is this zone is completely packed. That means when you inject the cement slurry with help of a compressor, right, the cement slurry cannot escape through the annular space because we have sealed, right. The cement slurry is injected, which will be focused into the surrounding formations, right. It cannot escape out through the borehole we have drilled. So thereby this particular zone is also now grouted. Then we take the packer to the surface and here we seal it, then the injection is done, right. So this is how the entire borehole is being injected by drilling a well right up to the bottom, and then we carry out injection by slowly withdrawing the packer to the ground surface. So this is how the surface has been grouted by locating different wells, right, at some frequent intervals the grouting has been done as shown in the diagram at all these locations. After having done this, this is expected to have improved the subsurface conditions, right. So, what we have done is, before grouting we did some seismic refraction survey. That means we are using hammer blow method at number of locations in the excavated site, and the average velocity which we could achieve was only, which we could measure was only 1200 meter per second. After that we did this substage grouting. After grouting, when we repeated, the velocity has increased by more than 2 times. It is nearly 3000 meter per second. So, this increase in velocity indicate what? We have improved the ground. That means without ground improvement, the velocity was very less, indicating the rocks are nearly not sufficient enough. They do not have the capacity enough to withstand the major structure that is going to come up here, right. After improving the ground, the velocity has increased to 2800 meter per second. This is how seismic refraction survey can be effectively used to see whether we have improved the ground, which is of great asset to geotechnical engineers, right. Then we can also understand weaker zones in the rocks by carrying out seismic survey from the boreholes, right. That means this technique is known as cross hole seismics. That means we use one of the borehole, right, to energize the ground. That means we use the source in such a borehole, right, and then we try to understand what is the impact of the energy which we have created on the adjacent boreholes by deploying what is known as the geophones at different locations in the borehole, right. So, this also helps us to know or assess the soundness of the basement rock, right, where we are going to construct a major building of some strategic importance, right. For that we need to clearly characterize and understand the subsurface formation. So, this technique can also be used to understand the efficacy of the ground improvement. For example, if we have done grouting in the borehole here, right, how effectively we have done grouting can be also estimated by firing a shot or generating shock. The shock waves are traveling through the formation which is sensed by the geophones here. So, this is how we can also deduct how we have improved the ground by grouting method, right. So, what we do here is something like what we see on the diagram here, right. We use a source. This source can also be a simple hammer, right. A simple hammer can be used as a source. This source will activate, will generate some energy. This energy is transmitted through the formation. On the other end, in the adjacent borehole, in this case we are using 2 boreholes, right. In the first borehole, the detectors are kept. The second borehole also a detector has been kept, which is a geophone, right, basically a geophone, right. So, these 2 holes are receiver holes and this is the source hole, right, and we try to understand what is the velocity in the formation. So, this method is much more direct method, whereas in seismic refraction method this is the source, we had the geophones, receivers are kept at different locations, the shock waves go in and get refracted back, isn't it? Whereas in this method it is directly we have gone down below the surface of the earth and then we are energizing the ground. The effect of this energy is measured in some nearby boreholes. That is why it is called as borehole seismics. And in India, there is a code of practice. BIS has given a code of practice for conducting seismic testing, right, especially between boreholes. Already I showed you the seismic standard for carrying out seismic refraction survey, whereas ASTM has got standards for both refraction as well as reflection survey. In the case of India, there is also a separate standard for conducting borehole seismic method. The standard is 13372, right. And what are all the instruments that are necessary to conduct the seismic cross-hole test, right? We need a source and a geophone, right? A source and a geophone are necessary, right? However, we also need some additional facilities such as a pulley and a tripod system. This will be kept over the borehole and the tool will be lowered slowly into the borehole. And the geophones that are used for cross-hole seismics is specially designed because in the surface geophone we had seen already. A geophone is something like this with a long spike. We used to push the geophone into the earth, right. So, the surface geophones are firmly grounded with the help of a spike system. So, it has got a firm contact so that it can pick up the signals that are received. In the case of borehole, we are going to keep the geophone something like this. It is attached to a cable, right. So, the geophone need to be firmly touch the wall of the well, right. This is a bore well, right, borehole, ground surface, this is the well, right, and the geophone need to firmly, it cannot freely hang at the center as you see in the picture now. To facilitate that, we use some special packing system. That means on the side of the geophone there will be a kind of inflatable balloon, or in some geophones you may have a kind of lever mechanism, right. That means after taking the geophone to the desired level and you can activate that tool so that the geophone will be pushed towards the wall of the borehole, right. So, this arrangement is necessary when you conduct a cross-hole seismic. So, in cross-hole seismic, the geophone which we use is designed differently with this arrangement. That is why the borehole geophones are expensive than the surface geophones, right. In the picture you will see. So, here what we see is two boreholes. First of all, to know whether the borehole is drilled perpendicularly, vertical, we also conduct, to know that we conduct a inclinometer, and here is the hammer which is a source, and as you see, as I told you previously, we have a packer. This, with the help of this packer, we have made the tool to touch the wall of the well. Now, we have energized the ground with the help of a hammer blow, right. What is the hammer blow? This particular tool which was at some height, which is allowed to fall, right. The part of this hammer is allowed to fall. That means it has got two parts. One is the bottom and another part is lifted up, right, and allowed to drop. So, this is like a giving a hammer blow. This hammer blow generates shocks which are transmitted through the formation, right, which are sensed with the help of a geophone. The geophone also has a inflatable packer system. With the help of this packer, that means we pump in some gas or air, this will inflate so that the geophone firmly touch the wall of the well. So, this is the special arrangement that is necessary to carry out borehole cross-hole seismics, right. That means we had two boreholes. First, we check the angle of the drilling, right. That means whether the there is any slope that is sensed using a inclinometer. It is a special tool that is used to know the verticality of the borehole. Then this is the source, and here are the geophone. Then both of them are packed so that they touch the surface. Now we are going to give a hammer blow. Yeah, this is what has been done. The weight has been dropped, that generates the signal. The signals are sensed here and which are recorded on the seismograph, which is the oscilloscope. With the help of that, right, we can determine the not only the distance, or we will be able to understand the shear velocity between these 2 points. So we will know, because we know the distance between the 2 holes, right, and we have the arrival time also. That means this is the time at which it was energized. This is the time at which we received the first major signal. So using this, we can determine the time of arrival at this particular location. We know the distance, so we can determine the shear wave velocity. Usually, we repeat this by keeping the geophone at different depths. First, second, 3, 4, this is number 5, then this is number 6. Is it clear? That means both the location of the source as well as the receivers can be varied, right? That means we are literally scanning. Suppose if the source is somewhere here and the detectors are kept at different locations, you may repeat, or we may have a multi-channel recording system. That means here this cable will have 5 geophones. So all the 5 geophones will simultaneously receive the signals as I am drawing, right. After completing this, then the source is moved from location 1 to location 2. Let us say the source is here now, right. From here shot is fired. So this is how the signals are getting transmitted. So this method is known as cross-hole seismic method. Sometimes we may also go in for downhole testing. Here we have a source at the surface, right. So as I told you, the source is kept at the surface, right, and when you give a blow to this source, right, usually we have a hammer blow, or we may also have a horizontal bar, right. Even sometimes the automobile which we use can be used to firmly, that means the car can be kept over this, the tire of the cars can be over this bar, so that this bar is firmly touching the ground. Then we can give a blow from the side. This generates energy, right. That means we are having only one borehole now, but the geophones are kept inside the borehole, right. Now we have a 2 geophone system. Energy is created here. This energy is going into the earth, which are detected at 2 locations. So here in the oscilloscope we have 2 recordings. This is for location 1, this is for location 2, this is location 2, this is location 1. So here we have the arrival times, right, from here to reach this place, how much time it takes, from here to reach the location 2, how much time it takes, right. So using this also we can determine the shear wave velocity, right, how much time it takes to reach different depths below the surface of the earth. So this method is known as downhole testing method. Here we are detecting the shocks that are transmitted at the surface at different depths. So this technique, as I told you, is called as downhole testing method, right. And why do we go for downhole testing? Sometimes the information which we require may not be very critical, and hence we have drilled only one borehole to understand the velocity, at different locations below the surface of the earth. Right. Now, as I told you in the previous slide, right, we have conducted survey using cross-hole seismics. That means we have scanned the section between the two boreholes, which means we have kept the source at 3 locations and energized, and the shocks are detected at different locations, right. So, these are all the locations of geophones. You can do this by having a multi geophone cable, or we can repeat, right. We can repeat. Suppose if you have only 4 geophones, we can keep 4 geophones here, make one sounding from this location 3, then lower the 4 geophones to the next level, then next level, next level. This is how also we can carry out the survey. So, ultimately what we have done is, we had the hammer kept at at location 1, geophones at different locations on the adjacent borehole. So, one sounding was complete. Then we shift the source to location 2, location 3. So, this is how we have carried out the survey, and we can interpolate the velocity at different locations, right. And using the interpolated values we have at different points in this section, right, especially in this zone, we can create what is known as a cross-hole velocity profile, right. So, here this is borehole number 1, borehole number 2, this is the source, this is the receiver, right. This is the source and this is the receiver well, right. From that we can plot a nice diagram showing how the shear wave velocity varied between these 2 boreholes, right. And we can also repeat by interchanging the receivers to this hole and source to the other hole. So, we can again take the average, right. So, this is how this cross section can be improved further. And why do we carry out a test on inclination of the borehole? So, here you can have a look at this case. This borehole is slightly inclined, that means it has got some angle here, right. Though we take all care during the drilling of boreholes, so depending upon the site conditions and the driller's ability, sometimes the holes are little bit inclined, which need to be considered by us, because we are estimating the velocity between these 2 locations, right. This is the distance between the 2 locations. However, this distance may vary at different locations of the borehole. As the borehole is, this borehole is little bit inclined, the distance x is high here. When you are somewhere here, the distance between the boreholes are little less. So, we need to use the correct distance to estimate the shear wave velocity. So, this is how seismic methods are used to understand the weakness or weak zones at some locations, as I showed you in a picture, right. This is the photograph taken at a location, right, where you can see the rocks are so massive, so nice here, whereas it is very weak at this location, right. This is the close up of the picture, right. So, in such locations we do cross hole seismic to understand the depth of this weakness. So, what we did is, we drill a hole here, we drill another hole here. This will be used as a source, this hole will be used as a receiver to determine what is the shear wave velocity at different depths. So, this is how we characterize whether this weak zone is extending to greater depth or not. So, these are all some of the applications of seismic refraction method. Toward the end, we had seen how we can conduct cross-hole seismics to arrive at such a nice seismic section. So, from the beginning, if I want to give you a recap, we started looking into seismic refraction method. First, we had looked into the seismic wave geometry, how the seismic waves are getting refracted back as head waves. Because it meets at critical angle, the shock waves are traveling at the velocity of the lower layer V2, which is here at the geophones kept at the surface. Then we had a look into estimation of thicknesses of layers for one layer case. Then we had seen for two layers and multi-layer. And if the formation is inclined, that is dipping, we can determine the dip angle also. How? By carrying out shooting from down dip and then another shooting from up dip side. Using this time difference, we can estimate the angle of dip. Then we had a look into what are all the different arrangement of shooting, such as profile shooting, fan shooting and arc shooting. Then we had a look into some applications of seismic refraction method. Toward the end, we had seen today how we can understand the efficacy of the ground improvement procedure we had followed at the site. Toward the end, we had a look into carrying out survey in the boreholes, that which is known as cross hole seismics. So this would have given you some insight on the application of seismic refraction methods. Thank you so much.